Thank you. Okay. Yeah, thank you very much to everybody. It's really nice to see some old friends here, and I hope this talk will be interesting. I talked about some of this material at the last conference, but we've done a lot since then. So so this first slide shows that I'm on the other side of the world from Russia, but not very close to anybody. I'd like to first pay my respects to Sergei Feofilov. These are pictures from the DPC conference in 2019, and so it was very nice to have Sergei here, and I was very sorry to hear of his passing. And this is some of our group. We have been exporting some of them lately, and we are trying to import some more now that it's possible, as COVID is getting less. So my work is in collaboration with John Wells, who runs the experimental part of our program, and my role is more in the data analysis and modeling. And we have some famous alumni at Canterbury. One of them, Ernest Rutherford, before he invented nuclear physics, he did experiments on high frequency magnetization. So maybe that's some condensed matter physics, even if it's not spectroscopy. And of course, Brian Wyborn was a student and then a staff member here. And relevant to some of this material, Roger McFarlane was very famous in the spectroscopy community for work on coherent spectroscopy. Now, I think everybody here is familiar with the Deca diagram. This is the updated diagram by Carnal. And so it was very important in the 1960s and onwards to classify the energy levels of lanthanide ions and to learn about the energy level splitting and the radiative and non-radiative processes. And that is what enabled many applications. And we hope now that some of the more challenging applications that people are trying to work on to do with single ions and quantum computing, we hope to help that by providing some better insight into the electronic structure and really how to understand these calculations, because they become very complicated in some of these systems. So the electronic structure, the overall electronic structure is the same no matter what host crystal you put these ions in, because the Coulomb interaction and spin-orbit interaction are very large, and the crystal field interaction is rather small. Then there are some other interactions that we don't think about so much. Perhaps there's the Zeeman interaction. That's one interaction we can control. We can apply a magnetic field. We could also apply an electric field as well, but magnetic fields have been very important because they split up Kramer's doublets and then allow all kinds of interesting experiments and devices to work. And then there's also the hyperfine part of the Hamiltonian. The main part of the hyperfine Hamiltonian that's relevant to most of these ions is actually involves the interaction of the electronic states with the nuclear spin, either the quadrupole moment or the magnetic dipole moment. But in some ions, most importantly europium, where you have total angular momentum of 0, those electronic effects are small, and so the direct interaction of the nucleus with the magnetic field and the lattice are actually very important in that case to understand what's going on there. And of course, the crystal field Hamiltonian is essentially a way of understanding and representing the potential that the F electrons are feeling. It's not really an electrostatic potential, it's a much more generalized potential. And in YSO, there are 27 crystal field parameters if we count real and imaginary parts. So it's been very challenging to try to work on this model with these in these systems. You're all also familiar with the idea that these parameters that parameterize the interactions vary across the series in a predictable way, and that's what enabled the understanding of hosts like lanthanum trifluoride, lithium yttrium fluoride. We were able to work our way across the series and use parameters determined from one ion to estimate the parameters for other ions. And I also like to think that expressing things in terms of parameters is actually much more useful than just knowing the energy levels, because otherwise it's very difficult to compare what's happening in europium, for example, with what's happening in erbium. They have completely different electronic structures, but the parameters are not so different. Some of the earliest work on coherent effects was done by Errol Hahn in the late 1940s. And of course, NMR went from being an interesting piece of physics into chemistry, understanding the structure of molecules, and then into medicine, doing nuclear magnetic resonance imaging, all making a lot of use of these coherent spectroscopy effects. Now, based on the pioneering work of earlier researchers such as Roger McFarlane, Matt Seller's group in Australia managed to demonstrate that they could store coherence in europium ion doped into YSO and retrieve that the coherent signal in 6 hours later. Essentially, that's a spin echo with a lifetime of 6 hours. And on the bottom right, this is Manjing Zhong. She was the lead author on the paper. She's a student, and she's now back in China. So the basic spin echo that they were seeing has a T2 of about 20 seconds. And then by these clever RF pulsing techniques, they're able to extend that to a very, very long time. But the key thing that is happening here, I'm sorry, I can't make my, there it goes. The key thing that's happening here is they're working at a magnetic field and a direction which gives them what they called a Zaphos point. It's sometimes called a clock transition in other areas. So small perturbations in magnetic fields from spin flips in the crystal don't change the energy to first order at those points. And that's what's allowing the very long coherent lifetime. And to be able to do this, you have to understand the electronic structure. In this case, they were using a spin Hamiltonian, which is quite adequate in this case. But if we want to work in areas, things where the spin Hamiltonians might break down at high magnetic fields, for example, it's useful to have a crystal field calculation instead. So YSO has 2 sites, a 6 coordinate site and a 7 coordinate site. This complicates things because we have to work out which energy levels, which lines in the spectra go with which of those sites. And one of our students, Sebastian Horvath, did a very thorough job of working out how to do calculations for this system a few years ago, wrote some new code to do this. And the way this worked was to put together both electronic energy levels, just measured with conventional spectroscopy, ground state, paramagnetic resonance spectroscopy, these rotational curves. This comes from looking at the 1.5 micron transition and rotating the crystal. So it's giving information about the ground state and the excited state, and also some Raman heterodyne to really understand the very complicated hyperfine structure. And so so the fit was to all of the crystal field parameters, about plus a few free ion parameters. I've lost the number here, but it's 34, about 34 parameters fit to the order of 100 real data points. So that was for one particular site. That was site 2, the 7-coordinate site. And that was mostly based on literature data, apart from this Raman heterodyne work, which was done at Otago in Jevon Longdale's lab. So having started that, we really started a project of trying to look at several of the ions across the rare earth series. This data here happens to be for samarium, but what we've been doing is we had a magnet and a Fourier transform spectrometer, and we can easily mount the crystals in three different orientations, so that we're measuring the splitting along 3 different axes. And this, as I said, this is for samarium, and just 3 different axes isn't actually enough for a low symmetry site. You really need at least 6 different axes. So for samarium, Nicholas Jobbett did some additional work using Raman heterodyne. But he was able to measure transitions, Zeeman splittings to dozens of levels for each site. So it's a lot of information about the magnetic splitting. And then he went back and worked on erbium some more, measured, again, dozens of magnetic splittings along the 3 axes for both site 1 and site 2. And one of the things I wanted to emphasize here is that the magnetic splittings, this is the magnetic splitting of the ground state of erbium in site 1. Some of these things are very anisotropic, and this has a maximum G value of about 14. And having those measurements allows us, in a sense, to orient the crystal field Hamiltonian. If we didn't have the magnetic data, then you couldn't fit the crystal field parameters, because they would just the energies alone is not enough to fit all of those crystal field parameters. So these are this is a table of parameters, which I don't expect you to read, just to appreciate the sheer number of parameters, the crystal field parameters for site 1 and for site 2. Now, the next thing we did with this was to try to make some predictions. This is data from a very nice experiment, Petit et al. As you may know, the YSO crystal is it's very difficult to measure polarization because the crystal itself will cause changes in polarization. But by making a circular crystal with the oriented along the B axis of the crystal, the only symmetry axis of the crystal, they're able to rotate the crystal and measure the response, the absorption as they rotate the crystal. And depending on whether E is parallel or perpendicular to the B axis, the variation will be a variation in either magnetic dipole or electric dipole transitions. So the blue lines are variations which we can attribute to magnetic dipole, the magnetic dipole varying. The red ones we don't really know how to calculate yet. But this is our calculation comparing the magnetic dipole with the magnetic dipole intensity with the experiment. Sebastian Horvath's first work on site 1 gives a variation that is out of phase with the experiment, but once we added more data, it came back into phase. For site 2, we're still out of phase in our calculation with the experimental data, but some of the work that people have done in Australia suggests that there may be some kind of problem. They may have got their angles mixed up for site 2. Remember, all of these calculations obviously fit the magnetic splitting in the ground and excited states, the G tensors. But this measurement is probing the magnetic dipole moment between the ground state and the excited state. So it's something that's not actually being fitted to. There's also some interest in using erbium at very high fields to do certain types of pumping schemes. And that's a very non-linear regime where the spin Hamiltonian approach is breaking down. There's mixtures between the electronic states. And so this is a calculation comparing our calculation with the measurements that Miloš Ranjic made. And that work is continuing in Australia. So we've been working our way across the series. We've done a little bit of work on cerium, some quite thorough work on neodymium and samarium, and also some work on holmium, where we can see the magnetic splittings and the hyperfine splitting with the FTIR. And so that's obviously a very interesting system that a lot of people in the audience have worked a lot with those holmium transitions. Now, I wanted to briefly talk about how can we understand these calculations and these fits, and can we relate them to quantum chemical calculations? So some of my colleagues, especially in China, have made use of techniques pioneered by Seo's group, where they use a DFT calculation to create a potential, a quantum mechanical potential, and then they embed a cluster in that quantum mechanical potential. And the thing I encouraged them to do was to use these calculations to work out the crystal field parameters rather than just work out energy levels. And it's actually, for cerium, it's not actually very difficult because there aren't very many levels and we can project out the Hamiltonian. We can't just use the energies because there's not enough of those. But if we work out the entire Hamiltonian matrix, we can fit that to the crystal field Hamiltonian. And briefly, you know that this is the Hamiltonian equation, the eigenvalue equation, HV equals VE. And of course, you can solve that for H. If instead of knowing H, you know the eigenvectors and the energies, you can solve for H. So we can take the subset of energies and eigenvectors from the ab initio calculations and really do the same thing. Now, there's some subtleties here. If you don't do it properly, you end up with a non-Hermitian Hamiltonian, but it's actually quite easy to orthonormalize that and get an effective Hamiltonian that is Hermitian, and then just solve for the crystal field parameters. So this is an example for lithium yttrium fluoride, comparing calculations for cerium with experimental data for praseodymium 3+, which has a reasonably good agreement, tends to overestimate the B20 parameter. This group went on and showed that in YSO, they could tell which of these G tensors come from the 6 coordinate and the 7 coordinate site. Actually, the G tensors are from LSO rather than YSO. But it's quite striking that they can use the calculation to work out which is which. So there's one of the sites that has a principal value that's almost vanishing, and the other one doesn't. And so they can see there's a difference there. And so I asked them to do some more calculations on this. And the difficulty with having 27 parameters is it's very hard to visualize what's going on. And so I've been trying to visualize this by visualizing the potential. So this, if you had a very simple crystal field Hamiltonian with just a B20 parameter, you'd have a potential that looks like this, with a positive, blue is positive, red is negative, blue is positive. And then similarly for combinations of 1 and -1 and 2, 2 and 2 -2. So these are potentials, and they are applied to the 4f orbitals. So don't confuse this with an orbital. It's just the potential, the second rank part of the potential. And so if we compare the parameter fit for erbium with the ab initio calculation for cerium, instead of looking at these numbers, we can make this little picture. And you can kind of see, and it's similar with the numbers, that there's some misorientation between these two. The B20 is a little bit too large. So that was site 1. Site 2 looks quite different. You know, it's positive, negative instead of negative, positive. You can see the signs of that B20 are different. So that is promising, but when we do the same thing for the rank 4 and rank 6 crystal field parameters, they don't actually match up particularly well. So and it's very difficult to tell at this point whether that's a problem with the calculation or a problem with the fit or some other problem. But really there's really an unanswered question here of how do you compare the parameters when you have so many of them. This is for site 2, and in this case, actually the rank 4 parameter fit and ab initio calculation look quite similar. So I think I should wrap up soon. I just wanted to mention 1 or 2 things. We're now working on making micro and nano crystals, which are useful because it's easy to make them compared to growing YSO, which needs to be grown as a crystal at 2000 degrees. It's quite challenging. And we're also working on europium, which is challenging because the direct interaction of the magnetic field and the lattice with the nucleus is actually a very large effect, and it's actually dominant for the D0 I don't really have time to talk about that in detail. That's where we are with trying to simulate the D0 and F0 G tensors of europium, and we're making some progress there. And I would say there's a paper that one of our former students has published, Karen Smith, on crystal field calculations in europium, not in YSO, but in some quite low symmetry systems. So in conclusion, we're working our way across the series. We've done some modeling in all of these systems. There's a Chinese group who's independently been working on YB3+. And I want to emphasize again that the magnetic data is really necessary in order to do this work. And so these are some of the things that we're trying to work on. We're hoping to do a lot more on europium and praseodymium in the near future. So I think we're still connected, and so I want to thank the organizers again for inviting me to talk to you, all of you, and I'm happy to answer any questions.
Okay, thank you very much for a very interesting presentation. Now, any questions, please?
May I ask a question?
Yeah, sure.
Yes. Do you hear me?
Yeah, yes.
Yes, Marina.
First of all, I would comment that this is beautifully done work. ISO is a very important and very difficult system for both experimental spectroscopy and for calculations with these two low symmetry centers. And it seemed almost impossible to do crystal field calculations until Mike came and did that. So it is once more very good experimental part done also in Australia and New Zealand, and theoretical part. And thank you for a very interesting talk. And I have such a question. You mentioned this comparison with ab initio calculations, but how the potential is chosen, I did not understand. It is rather a difficult task.
Yes. It's actually quite a complicated calculation. They do a reason. I mean, I'm not an expert on this, but there's a reasonably standard density functional calculation using the VASP. Happens to be using the VASP software, but then that is instead of using a Madelung potential, an electrostatic potential for the distant ions, they create an actual quantum mechanical potential from that calculation. I'm not an expert. Yeah, sorry.
What about exchange interactions?
Well, the main part of the interaction is a cluster which would include the at least the nearest neighbors. So that's done with a regular quantum chemistry program, the MOLCAS in this case. But this embedding, you need some sort of embedding. You need either a Madelung potential or this more advanced potential, and otherwise the calculation won't really work at all, I believe.
Okay, thank you.
Okay.
Okay, there was one more question.
So thank you for an interesting talk. I have maybe a naive question. how many fitting parameters you have in your modeling, because I see that your system is extremely complicated, so it is many multi-electronic system. So my question is, first, how many fitting parameters you have, and second question associated with first, what kind of physical considerations you have when you choose specific parameters of this fitting parameters? Could you explain?
Oh, okay. Well, you can see in this table there are 27 crystal field parameters if you count real and imaginary parts as separate parameters, and then there's the free ion, the Coulomb and spin orbit interaction parameters, and then there's two hyperfine parameters, one for the one for the magnetic coupling of the electrons to the nuclei, and the other the quadrupole coupling. So there's about 35 parameters. And about with the fitting, Sebastian Horvath made use of a reasonably modern fitting technique. It's a basin hopping technique. It's a little bit like simulated annealing, but the parameters are randomly changed, and then there's a regular fit done to find the local minimum, and then the process keeps going. So these parameters we didn't really start with some physical model because it just seemed so complicated at the time. So it was really just a fit, and then we've tended to when we start fitting another ion, we tend to use similar parameters and let them vary. But it's really, I mean, you're pointing out another very important point, that we really can't be sure that these are the global minima because the fitting space is so complicated. And I also suspect that there may be some sort of symmetries, not a geometrical symmetry, but some other kind of symmetry that may give you a very, very similar fit with some quite different looking parameters. And that's something that needs to be worked on, I think. But I'm not exactly sure how to solve that particular problem.
Thank you for a comprehensive answer.
Yeah, thanks.
Thank you. One more question. Okay.
Hello, I would like to ask a question. First of all,
Sure.
thank you for your interesting lecture. And I would like to ask which differences are you expecting to obtain for nanoceramics and microceramics results, and which approach are you going to use for introducing the grain boundaries, maybe, if you are?
Well, we've only really just started this. As I said on this slide, one of the main reasons we wanted to do this is that as you probably know, many of these crystals people tend to grow these crystals with very low concentrations, 0.01% molecular percent, for example. And that's very good when you're trying to look at something like the hyperfine structure. But in some cases, particularly in holmium, that low concentration crystal gives us a very weak signal for some of our other spectroscopy, for our laser spectroscopy, because the YSO has high frequency phonons, and so the excited states decay very fast. And so one of the reasons we wanted to grow some micro and nanocrystals is just so that we could do spectroscopy on higher concentration samples. And for that laser spectroscopy, we don't really care about the orientation. But then the other aspect that many people are working on now is putting putting nanocrystals into cavities to using cavity enhancement to do various experiments, and so that's another reason to try to develop this technique. And it's still quite difficult to make. I mean, making crystalline YSO is very difficult, but even these nanocrystals, we have to put them in an oven, heat them up to about 1300 degrees, and it doesn't always work. So it's still quite challenging to get that to work properly. I'm not sure if does that answer your questions?
Well, quite, yes. Thank you.
Okay, any more questions?
May I ask one more question?
Oh, certainly. Yep.
Mike, and what would be the difference in theory between bulk and nanocrystals? Do you plan to take into account some local field corrections?
Well, if we as far as the energies are concerned, when we compare, I didn't put them on this spectrum, but on this figure, because but the absorption spectrum for erbium, for example, is very similar. The nanocrystals give much broader lines, but we don't think that the structure is so different that the crystal field parameters would be significantly different. We've been trying to work on this in higher symmetry crystals with KY3F10, for example, because it would be interesting to see a difference, but it's actually very difficult to find much difference between the bulk and the nanocrystals. So at the moment we've just really been interested in the energies, but as you say, the nanocrystals could have very different, can have very different radiative and non-radiative properties, especially if they're very small.
Are there also differences in energy level positions?
Well, no, they don't seem to. Not really. They're usually in the same place, but the lines are much broader. The YSO, the inhomogeneous broadening, and for some of those erbium lines is below half a gigahertz or something, and that in the nanocrystals it's much wider.
Okay, and probabilities must be different. Thank you.